Hello, everyone. Please type in your full name into the chat, so that way I can take the attendance. Um, Actually, I plan to go to the lab next Thursday, and I mean next Tuesday during the class time. So you can go there also to pick up your Raspberry Pi and some other support components. So I will give you Raspberry Pi plus Sense Hat and also camera and some other push button, a breadboard. So those things to support your project. Okay, so next Tuesday, I will go to the go to campus to then you can come also to pick up your components, your Raspberry Pi and other components. Okay, so we'll do that. I will email you and email everyone to let everyone know. Okay.
What room number is this in?
What's that?
Room number? Do you happen to know?
I will email you, let you know. It
Okay.
should be 222. Yeah, but I will let you know in the email. Okay.
Okay, thanks.
All right, so let's just continue with the last time's slides. Last time, actually, I introduced several basic electrical circuit components. We saw resistors, we saw diodes, and also we learned the basic electronic theorem, which is the Ohm's law. We know Ohm's law actually give us the relationship between the voltage, current, and resistance. Okay, so that's the basic law for electrical circuits. Okay. And also last time we saw this LED, and we know LED is a kind of diode, but it's a light emitting diode. Okay, so I mean nowadays actually LED is widely used for a circuit to generate light as an indicator. Because a lot of time actually when you make a device, sometimes you need to have some kind of indicator. So LED is a very good choice. Okay? And and from last time we already know that LED is a polarized device. So it has two legs. And last time actually I showed you there are two legs for LED. One longer leg, that's the anode, the positive. And for the shorter leg, that's the cathode, which is is supposed to be connected to the negative. Okay, so this is a a typical circuit that we can have to drive LED, either light up or actually this one, if you just apply 3.3 volts to this circuit, then the LED will be on forever. Okay, so as long as you have the power applied. And last time we showed how can we calculate the resistance of this resistor, right? We use Ohm's law. So first of all, you have to figure out the voltage over the resistor, which is 2 volts, because you have to have 1.3 volts over the LED. And we know to drive a LED, you have to have 9 milliamps. So if you have 9 milliamps for the current, and for the resistor, we know for the LED, the voltage is 1.3. That means for the resistor, the voltage should be 2.0 because you know, the voltage, the summation of the two voltages on the resistor and the LED should be equal to the voltage source. Okay, so that means you use 3.3 minus 1.3, you got 2.0 for the resistor. Okay, so that means the resistance, according to Ohm's law, it should be V over I, and we know V is 2.0 volts, and I is 9 milliamps. Okay, and so it's equal to 2.0 volts over 9 times 10 to the power of negative 3 amps. Because, you know, for Ohm's law, you have to use amps, not milliamps. So you have to convert the milliamps to amps. So this actually, if you do the math, let me see. It should be equal to 2 over, it's about 222 ohms, okay? But instead of using 222 ohms, we use 220 ohms here. The reason is why? The reason is this. For resistors, okay, all those manufacturers, they just manufacture those resistors with standard resistance, okay? They don't generate, they don't manufacture you know, this kind of 222 ohms resistors. The closest standard resistor with the resistance of 220 ohms. So that's the closest standard value resistance. Okay, so that's why instead of using an accurate 222 ohms, you have to use 220 ohms, okay? Because that's the only available standard value resistor. Okay, so if you want to use an accurate 222, then you will have to order from the manufacturer, and that will make the price really high compared to a standard value resistance. Okay, so that's the reason why we don't use 222. Instead, we use 220 because 220 is the closest, you know, standard resistor. Okay, so this is the way that how you can figure out the resistance where you can use to limit the current, because you have to have a resistor. Without the resistor, if you directly apply the power directly to a LED, the current will be much larger than 9 milliamps. Okay, 9 milliamps to drive a LED must be, the current must be less than or equal to 9 milliamps. Okay, so if you have a current over 9 milliamps, you will burn the LED. So you don't want to burn the LED. That's why you have to use a resistor to limit the current. Okay, so this is how you can connect an LED to the circuit. And to drive a LED, usually you know, when you turn on a LED or turn off a LED, sometimes you want to dim the LED. So how to dim an LED? That means, you know, you can turn on the LED and make the light intense between fully on and fully off. Okay, so how to dim an LED? You use PWM signals. Okay, so PWM signals, and so this PWM signals actually basically they are square waves. Okay, so you can see here we have three kind of examples of PWM signals. Okay, so for PWM signals, we use duty cycle to describe their property. And this one has a 25 duty cycle, and this one has a 50 duty cycle. This one has a 75 duty cycle. And from the value, the duty cycle value, and also the figure, you can figure out, you know, what does the 25, 50, or 75 mean. Okay, so you can see 25 duty cycle. It means for each cycle, one cycle is from here to here. Okay, that's one cycle. Okay, so for each cycle, you see only 25% of time we have logic high, 3.3 volts. Okay, the other 75% of time we have logic zero. Okay, voltage is zero. So that's for the 25% duty cycle. So 25% duty cycle means only 25 of one cycle have logic 1. Okay, and in this case, in Raspberry Pi, logic 1 means 3.3 volts. Okay, for 50 duty cycle, it means 50% time we have logic 1. Okay, the other 50% of time we have logic 0. Okay, and for 75% duty cycle, that means 75% of time we have logic 1. Okay, other 25% we have logic 0. Okay, so you can see by changing the duty cycle of the PWM signal. So PWM signal basically is pulse width modulation signals. So you can see the width modulation signal means we can change the pulse width. Okay, so so 25%, you know, the width of the pulse width is only 25%, and for 50%, you know, you have half of the cycle has logic 1. Okay, so you can see by changing the duty cycle, we can change the length of the pulse or the width of the pulse. Okay, so if you have a 100% duty cycle, that means the whole signal actually you have a logic 1, 3.3 volts. Okay, but if you have a 0% duty cycle, that means, you know, all outputs are zeros. Okay, so you can see by changing the duty cycle, if we apply this PWM signal to here, instead of using 3.3, if we apply the PWM signal here, then by changing the duty cycle, we can change the intensity of the LED light, right? For example, if you output 0% duty cycle PWM, then the LED will be off. And if you output a 100% PWM signal on this line, the LED will be fully on. Okay. However, if you just output 70% of PWM signal, then your LED will be, you know, the light intensity will be between fully on and fully off, right? So that way you can dim the LED light. Actually, a PWM signal is very useful. There are several lags on the GPIO of the Raspberry Pi. They produce a PWM signal. Okay, and by using program, you can adjust the duty cycle to you know, to produce different duty cycle PWM signals. And then you can use this PWM signals either to dim the LED lights, or you can use PWM signal to change the motor speed. Okay, so you can use PWM signal to drive a motor, and then you use different duty cycle to change the motor speed. If you want to have a you know, a high speed motor, then you output 100% duty cycle PWM signal. And if you want to have a slow motor rotation, then you output like 25% duty cycle PWM signal. So that way you can by adjusting the PWM duty cycle values, you can change the motor speed, you can dim the LED lights. Okay, so that's the way that you control this kind of devices. Okay. All right. So once we know the LED, let's see. We have another kind of components we want to introduce: capacitors. Okay. So capacitors actually a lot of time they are used to smooth and decouple signals. Okay. So for smoothing signal, remember, most of the time there will be noise in the circuit signals. Okay? So to smooth the signal, that means to remove the noise, you can use a capacitor. Okay? Because capacitor actually can be looked at as a low pass signal, a low pass filter. For low pass filter, that means only low frequency signal can pass through, but high frequency signal will be blocked. Usually a noise actually is a kind of a high frequency signal. Okay, so we can use capacitors to remove those kind of high frequency signals. Okay, so a capacitor is a passive electrical component that can be used to store electrical energy between two insulated plates when there is a voltage difference between them. Okay, so I can show you what does a capacitor look like. Okay, let me see. All right. There are two kinds of capacitors. Two kinds of capacitors. Okay, so let me show you the So we have ceramic capacitor and electrolytic capacitor. Okay, so let me show you some examples. So this is a electrolytic capacitor, and this is a ceramic capacitor. Okay, so you can see we have and usually this ceramic capacitor has lower capacitance. Okay, but for the electrolytic capacitors, usually they have a higher capacitance. Okay, so that's these are two examples of the capacitors. Okay. All right. So you can see this is an example that we can use capacitor to smooth the signal and decoupling the signal. Okay, so remember previously we introduced the diode, and we know diode has a property that it only allows the current flow in one direction. Okay, so that means if we have a diode, if the power source is an AC signal, so the AC signal actually only the AC the current positive current can flow through the capacitor. For negative current, on this side, negative current will be blocked by the diode. Okay, so if we go back to that specific slide, you can see if we only have diode, then the output will look like this. Okay, the blue curve. The blue curve will be the voltage for the output for this load. Okay, because for the negative voltage, the diode will block it. Okay, because we know diode only allows one direction current flow. So how can we make this smoother? We can use this capacitor. You can see it's much smoother, right? Compared to the one we saw before, the blue wire. So the blue line actually is the output voltage for this circuit, because we have a capacitor. So capacitor actually is a kind of device that we can it can be charged. So basically, when the circuit the current flows through the diode, the capacitor is charged during that period. Okay, so at this time the capacitor is charged, and then when the current flow back, it will be blocked by the diode. But at the same time, because the capacitor was charged, so capacitor will discharge at this point. Okay, so that's why you see we have this blue line, because the capacitor is discharging. Okay, so this way, by having this capacitor, we can smooth the signal comparing to the one we don't have the capacitor. Okay, so that's why capacitor is very useful, very important for electrical circuits. Okay, and so there are two kinds of capacitors. We have a ceramic capacitor, small and low cost, and degrade over time. And electrolytic capacitors store much large amount of energy because it has more higher capacitance. Okay, so so you can see this we have this two kind of capacitors. I already show you the examples of these two kinds of capacitors. Okay, and to understand the number on the capacitors, you see the first number is the first digit of the capacitor value, and the second number is the second digit of the capacitor value, and the third number is the number of zeros. Okay, so this means you have 10 and followed by 4 zeros, picofarads. Okay, so this actually is for electrolytic capacitors. It's easier to know the value of the capacitance. So you just it's directly written on it. So it's 47 microfarads. It can endure 25 volts. Okay, so that's how you can know the capacitance. Actually, by using a DMM, a digital multimeter, you can also measure the capacitance for a capacitor. Okay. All right. So another very important components, electrical components, is called a transistor. Okay. So transistor actually is active device, active component. Okay. So transistors are one of the core ingredients of the Raspberry Pi microprocessor. Okay, so for any microprocessor, in fact, inside of the semiconductor package, there are millions of transistors. Okay, so their function can be used to amplify a signal or to turn a signal on or off. We can use a transistor as a switch. Okay, and so we need transistors to help us when interfacing them to electrical circuits that require large currents to operate. Okay, why we need the transistors? Because remember, for Raspberry Pi, in fact, for any kind of computer microprocessor or microcontroller, we cannot directly connect external devices, especially those high current devices like motors, to a microcontroller or a microprocessor, because microcontroller, they can only provide very low current. Okay, you already know what is current, what is voltage, right? So microprocessor or Raspberry Pi, the board, can only provide very low current. However, for a lot of external devices like motors, like even LEDs, they need higher current. So to drive a higher current device by using low current GPIO, we have to use the transistors, because transistors actually provides this kind of capability. Okay, so let's look at what is transistor. Let me find a example for you. Let me see. All right, so you see this is a diode actually. So for the diode, you see there is a black line here. That black line actually is showing you the polarity of the diode. Okay, so the current can only flow from this side to the side with the black line. Okay, so this is a diode, and this one is a transistor. So you can see transistor, it has 3 legs. You see, this is very small, actually. Transistors are very small silicon semiconductor device. Okay, so very, very small. One side is one side is round and the other side is flat. Okay, so it has 3 legs. And so you can see here, from here we have the picture of a transistor. So you have 3 legs, E, B, C, and so EBC. The meaning for EBC is the B means base leg, and C means collector, and E means emitter. Okay, so so you can see this is a NPN transistor. So the most popular transistor is NPN transistor. Okay, so this is B and this is C, this is E. Okay? So you can see B is in the middle, E and C. Okay? So in fact, the property for NPN transistor, you see, we have a current flow into B, right? It's called IB. IB is the current into base. And then we have current IC. IC, that's the current flow into the collector. And we have IE. IE actually is the current flow out from the emitter. Okay, so IE is equal to IB plus IC. And in fact, IB usually is very small. Okay, but IC is much larger compared to IB. Okay, so you can see from this property, you can understand that we can connect the base to Raspberry Pi, because we know Raspberry Pi actually usually it cannot provide very high current, and so the low current can flow into B because B only needs a very low current to drive it. Okay, but C, IC, and IE, the current is much larger. So we can use this large current to drive motors or LEDs or other high current devices. And the low current leg, which is the base leg, can connect to Raspberry Pi. So you can see Raspberry Pi only need provide a very low current, and then you can drive a high current to drive a high current device, right? So that's the beauty of transistor. So transistor can help the Raspberry Pi or other microprocessors to drive high current devices by only using a small current. Okay, so the small current is from the Raspberry Pi and flow into the base, and then the high current will drive a high current device connected to C or E. Okay, so that's why transistors is so important, so popular in electrical circuits. Okay, and so in fact, transistors, they can work as switches. So you can see in this case, if we apply, because transistor actually, I don't want to spend too much time to confuse you, because if you don't have the background of electrical engineering, the property of transistor is pretty hard to explain. But you can understand this. When we have a very high voltage for B, that will saturate C and E, which means C and E will be equivalent to a closed circuit. Okay, so if we have, for example, if we apply 3.3 volts, then the C and E will be considered as a short circuit. Okay, so that means current can flow through C directly to E, which means we turn on the switch, right? If you consider C and E as a switch, okay? And if we have a voltage of 0 on B, that means C and E can be considered as an open circuit, okay? So that means we don't have any current flow from C to E. So you can see this is another beauty property for transistor. So we can use a transistor to work as a switch. It's not a real switch, but it is equivalent as a switch, right? And the switch can be controlled by applying different voltage on this side. If we apply 3.3, then it becomes a closed switch. And if we apply 0 volt on this side, then it's an open circuit. So that's another very useful or very important property for transistors. Okay, so let's see. By using a transistor as a switch. Okay, so you can, in this example, we can connect a resistor to the B leg, and we connect a resistor to C leg. Through the resistor, we connect to 5 volts. Okay, so for B and C, they use different power supply. Why is that? Because for B, actually, the power supply is from the Raspberry Pi. And for C, actually, the power supply is used to drive a high current device. Okay, so you don't use the power on Raspberry Pi to drive a motor, because the power on Raspberry Pi is it only provides very low current. If you use that device, that voltage to drive a motor, you will burn the Raspberry Pi circuit. Okay, so you have to use a separate power to drive a motor. Okay, so that power actually is connected to C and E, and you can consider this as a motor. Okay, so that's and so you can see, by applying a very low current on B on base, you can produce very high current on C. That's the IC. So you can see red curve, that's for IB, the current on B, and blue curve, that's for IC, that's the current on C. Okay, so you can see you can use very low current drive by using, with the help of the transistor, you can produce very high current on the C side to drive a high current device. Okay, so this is very useful, very important for you know, why we use transistors in electrical circuits. Okay? So transistors actually are very important. In fact, if you look at the microprocessor itself, there are millions of transistors inside of the, you know, the semiconductor package. Okay. And this is the frequency response. Frequency response means if the input signal is a square wave. Okay, so this 500 kilohertz, 1 mega kilohertz, that tells talks about the frequency of this square wave. Okay, so the frequency of the square wave is 500 kilohertz, 1 mega kilohertz. So you can see actually this blue line, they are the the output signal of the transistor. And so you can see the frequency response of BJT transistor is not that good. Okay, when the input signal is only 1 megahertz, 1 megahertz is not a very high frequency. And you see the frequency response is, you know, loses the wave shape of the square wave. Okay, so for a high frequency input signal, instead of using this BJT transistor, we will use this FET transistor. Okay, so FET transistor is another kind of transistor. It's called field effect transistors, but it's still a kind of transistor. Okay, but you know, usually we use a different symbol to represent. You see, for BJT transistor, we use this symbol to represent, and for FET transistor, we use this symbol to represent. But anyway, they all have 3 legs, and in this case, we don't call it BCS, BCE. Actually, we call it GDS. Okay, but they are, you know, pretty similar. Okay, so so we can also use FET to work as a switch. And if you look at the FET transistors, the frequency response is much better. You can see for 1 megahertz, 5 megahertz is much better compared to BJT transistors. Okay. Okay. So we have introduced capacitors, LED, and also transistors. So this is another components that we can use for electrical circuits. Okay, it's called optocouplers. So optocouplers actually is very useful if if you have two separate circuits. If you have 2 separate circuits and you want to send a signal from circuit 1 to circuit 2, and you don't want to, you know, because a lot of time actually if you directly connect these 2 circuits together, you can circuit, I mean the noise in circuit 1 will be passed to the noise in circuit 2, right? So that's sometimes we want to separate them. We don't want to you know, propagate the noise from one circuit to another circuit. Okay, so to separate the 2 circuits, but at the same time we want to send signal from one circuit to another circuit. So, you know, this kind of optocouplers, they are very useful. Okay, so you can see, look at this figure, you can understand. So signal from one circuit will be passed through this LED. So the LED will generate lights, and the lights actually will be picked up by this light sensor. Okay, so this is a kind of light sense transistor. Okay, so by picking up the lights, this transistor can convert the light into current. Okay, so the current will output to, you know, the next part. So this coupler, actually optocoupler, actually is a very useful components if you do have this kind of requirement for your circuits. Okay. And other kind of electrical circuits components are switches and buttons. So I have let me see. And next Tuesday, actually, you will get this kind of buttons. So you can use this button to work on some interesting project. Okay, so I can show you this button. So this is a small button. You see, it has 4 legs. Okay? So the button actually, you know, it's just a push button. When you push the button, 2 legs will be shorted. Okay, if you don't push the button, those 2 legs will be open. Okay? So you can you know, insert the button into breadboard. Okay, so that way you can make your own circuit. Okay. So next Tuesday, actually, you can go to the lab to pick up your components. So for the components, you will have a push button and a small breadboard with the Raspberry Pi and SenseHead and some cables and a camera. Okay, so that's that will be all the components that you can pick up from the lab. Okay. So there are, I mean, the push button actually I showed you, that's only one kind of push button. There are, you know, many kinds of push buttons. So here on this slide, actually, I showed you several different kind of push buttons. Okay, so yeah, this is hysteresis. Actually, it's also a kind of you know, it's a kind of high power components. So you know, usually this kind of device actually is not that widely used. Okay, so let's just skip this. So the last kind of electrical devices I want to introduce are logic gates. Okay, remember in digital logic circuit, I don't know whether you have digital logic circuits knowledge, but for logic gates, in digital logic circuits, you will learn a lot of logic gates. You have, you know, there are AND gate, OR gate, or, you know, or a NOT gate. Okay, and exclusive OR gate. Okay, it's XOR gate. So we have, you know, many kind of logic gates. Okay, if you learn logic circuits class, you will know what kind of gate it is. For AND gate, it works as you know, if you have 2 inputs, A, B, C is the output. Okay, this is the truth table for an AND gate. Okay, so if both inputs are 0, then the output will be 0. And if we have 0 on A and 1 on B, the output is also 0. Okay, so 1, 0, and the output will be 0. 1, 1, the output will be 1. Okay, so this is the truth table for AND gate. And in fact, in circuits, actually, the logic gates usually they are packed in integrated circuits like I showed you last time. Actually, so this like this. Okay, so for logic gates, usually they are packed into integrated circuits like this. Okay, so that's for logic gates. Okay. So there are all kinds of logic gates. Like I said, you know, you have we will have AND gate. So 7408 is a package for AND gate. So in this package, you see there are 4 AND gates packed in this package. Okay, these 4 AND gates actually they don't have any relationship to each other. Okay, so if in your circuit you only need 1 AND gate, so you can choose anyone. Okay, so and on NAND gate, this is the symbol for AND gate. Okay, so whenever you see this, you know it's an AND gate, and this is the truth table for AND gate, and this is the the package for AND gate. So if you need AND gate in your circuit, you just need to purchase IC chips 7408. Okay, so 7400, that's for NAND gate. You see there is a N in front AND. Okay, so that's why we call this NAND gate, because you have a circle here. This circle indicates that's a NOT. Okay, circle means NOT operation. Okay, so that's why you see instead of AB, there is a bar over it. So the bar means NOT operation. Okay, so you can see if you compare the truth table of this, these two truth tables, you can see for AND gate, 0, 0, the output is 0, 0, 1, output is 0, and 1, 0, output is 0, and 1, 1, output is 1. Okay. However, for NAND gate, it's totally, completely, opposite. Okay. So 0, 0, you have 1, 0, 1, you have 1, 1, 0, 1, 1, 1, 0, because you have this NOT operation. Okay, so a NOT operation actually is a NOT gate. So the NAND gate actually is equivalent to this. Okay, a NAND gate is equivalent to an AND gate with a NOT. Okay. Okay, so a NAND gate is equivalent to two gates, one AND gate and one NOT gate connected in serial. Okay, and this is a NOT gate. So for NOT gate, the number, actually these numbers are standard numbers. Okay, so that means for example, if you want to build a circuit, in your circuit you need a NOT gate, so you just need to find 7404. Okay, so you can search for 7404. You purchase this kind of package. So this kind of IC circuit, you see inside of the package, you have 6 NOT gates. Again, all these 6 NOT gates, they don't have any relationship to each other. So you can use either any one. Okay, and for NOT gate, this is the truth table, and this is the symbol. Okay, and this is OR gate. So OR gate, this is the symbol, and this is the package. Is the IC number is 7433. So that's OR gate IC circuit. Okay, and in this OR gate IC circuit, there are 4 OR gates, and this is the truth table. And so for OR gate, only when both of the inputs are 0, the output is 0. Otherwise, the output is 1. Okay. And we have NOR gate. So NOR gate actually is the same as the NAND gate, but is a OR gate connect to a NOT gate. Okay, so this is yeah. So that's the meaning for OR gate. So that's why for OR gate, if you compare OR gate to NOR gate, you see the output is completely opposite. Okay. And one more gate is called XOR gate, exclusive OR gate. And exclusive OR gate, this is the symbol. Okay, so you can see the symbol. This is the symbol. So for symbol, so for XOR gate, exclusive OR gate, you can see if you compare to OR gate, there is one more curve here. Okay, so that's OR gate. And to represent OR gate, you use this. Exclusive OR gate is XOR gate. So for XOR gate, you use a circle with a plus sign to represent the exclusive OR gate. Okay, so number for the IC package is 7486. So there are 4 XOR gates inside of this single package. And look at the truth table of XOR gate. So for the truth table of XOR gate, so think about the name for this gate is called exclusive OR gate. Okay, so you can see only when the two inputs are different, the output will be 1. Whenever the two inputs are the same, then the output will be 0. Okay, so this is very, very interesting. Okay, a lot of applications actually can be implemented by using this XOR gate. Okay, so this is these are some logic gates, and so from this slide actually is this slide actually is very informative because it shows all the symbols, all the the package and the truth tables for almost all those logic gates. Okay, IC numbers, truth tables, symbols, so it's a very good slide. You see, this is a example of 7408. So 7408 is AND gate, right? So there are 4 AND gates inside of this 7408. Okay. So there are, and this actually is an example for another kind of device, is a flip-flop device. So you can see this are flip-flop. So in this package, we have 2 flip-flops. Okay. So flip-flops actually they are very important devices that we use them to build SRAM. SRAM actually they are the a fast memory device, and so if you already know, in computer system we have cache. Okay, so cache is a kind of fast memory device. Okay? Most of cache they use flip-flop to they are built from flip-flop. Okay, and for logic gates, actually, they have different kind of logic gates. You may have TTL, you may have CMOS. Okay, so TTL, CMOS, they have different meaning for logic 1 and logic 0. Okay, so that means when you build your circuit, if you use different logic gates, you have to make sure that they can understand each other. Okay, because for TTL gate, you see, TTL gate, the input from 2 to 5 for the input will be considered as logic high, logic 1. Okay, from 0 to 0.75 will be considered as logic 0. Okay, so you see CMOS actually is different. The input, for input, only when the voltage is greater than 3.5 will be considered as a logic high. So you can see for TTL gate, if you have a 2.5 input, then TTL gate will consider that input as a logic 1. However, for CMOS, it's not. Okay, so you can see that's the difference between TTL and CMOS. So whenever you try to make your own circuit, if you want to use logic gates, you have to make sure that you use the same logic gates. If you use TTL logic, then you use TTL for all other logic. Okay. If you use CMOS, then if you choose CMOS, you use CMOS for all. So that's that way you don't have this kind of mismatch of the logic levels. Okay. Another very important thing for electrical circuit is called floating inputs. So what does floating inputs mean? You see, look at this example. Okay, so we have this 7408 AND gate. So for this AND gate, we have 2 inputs, right? Input A and input B, and we will switch to control whether we connect to input A or whether we can connect the voltage to input A or input B. Okay, so the output will be used to drive this LED. And again, you have to have a resistor. Okay, so if you don't have this resistor, you will burn this LED once you close the switch. Okay, so if we for AND gate, remember, whenever the there is input, I mean only when both of these inputs are ones. So if you close this switch and this switch, so you will have logic 1 here, logic 1 here. So 1 1, the output will be 1. So the LED will be on, right? If you open one switch but you still have another switch here, so that will create a problem, because for this one is okay, you have 1, but for this one, you see we have a float input. For float input, that means floating input, that means the input doesn't connect to anything. So we don't know what it is. We don't know whether it's 0 or 1, right? Because it's floating. It doesn't connect to the power. It doesn't connect to the ground either. Okay. So this kind of problem is called floating inputs. Okay. So for floating inputs, actually, we need to avoid this kind of thing. So how to avoid this kind of thing? We use pull up or pull down resistors. Okay. So from the name, it's very easy to understand. Pull up resistor means the resistor is connected to the voltage. And for pull down resistors, that means the resistor is connected to the ground. Okay. So instead of leave this two legs connect to nothing, we can either use pull down resistors or pull up resistors. Okay, so you can see in this case, when we use pull down resistors, the other side we connect to the power. Okay, so if the switch is open, you can see this leg actually is connected to the ground. So that means you have a 0. However, if the switch is closed, you see, because when we close the switch, this leg is connected to the power. So it becomes logic 1. Okay. But the other side is still connected to the ground. However, remember, from the Ohm's law, even though it's connected to the ground through this resistor, because the voltage will be fully load onto the resistor. So that means at this point, it still has a 3.3 volts. Okay, so that means it's a logic 1. So you can see by using a pull down resistor, the same thing for pull up resistors. Okay, so for pull up resistor, if the switch is open, then you have a logic 1 here. Otherwise, if you close the switch, because this side is directly connected to the ground, you have a logic 0. Okay, so in this case, no matter whether the switch is closed or open, you have a specific logic level. You don't have floating lag. Okay, so that's the usage of pull up and pull down resistors for electrical circuits. Okay, and we have some kind of interconnecting gates. Okay, so this kind of circuit, you can see in this circuit, you have gates, you have diodes and FET transistors. Okay, so this kind of circuit is logic gates actually are interconnected to other logic gates and components. So how can you deal with this? Actually, if you want to learn how to interconnect gates and other components, you can go to the textbook to learn the details. Okay. So let's just skip this. Another very important device for circuits is analog to digital conversion. It's called ADC. Okay, so if you search ADC, you will find that ADC actually is very important. And also we have DAC. DAC means digital to analog conversion. Okay, so why we want to do this? Because there are a lot of, remember, computer system, they are digital circuits, okay, digital device. So, but a lot of real signals like sound, pictures, they are analog signals. So to make sure that the digital device can process analog signals, you have to convert analog signal to digital. So that's why you need ADC. So ADC is used to convert analog signals like temperature. So for example, if you have a temperature sensor, the signal captured by a temperature sensor is the temperature. So the temperature signal actually is a kind of analog signal. Okay, so you need to convert this analog signal into digital. For analog signal, it means continuous signals on, for time, this amplitude. Okay, and for digital signals, actually, it's discrete signals. Okay, discrete signals. Okay, so computer can only process discrete signals, but for real signals, there are analog signals. So you have to convert analog signal to digital signal to let the computer process it. Once your processor process the data, you have to output the data back to analog devices, right? For example, if you want to play your music actually, your speaker is a kind of analog device. That means it needs analog signals. Okay, so but the sound, the music recorded on the CD, they are digital signals. So how can you play a digital signal on a analog speaker? You have to use DAC. DAC is used to convert digital signal into analog and then play the analog signals. Okay, so these are two kinds of very important devices for electrical circuits. Okay. This is the last components that we want to introduce. Is called optional amplifier. So optional amplifier actually is a kind of amplifier. It can enlarge the input signal. So if you have a very small signal input, the output will be very large. Okay, so that's we call amplifier. Okay, so as computer science students, you only need. We do have this kind of device, but I don't want to throw too much information to you to confuse you. Okay, but this is a kind of amplifier that we can use to amplify the input signal from a very small signal to a large signal. Okay, like if you like music, you have speaker, right? So the speakers actually you have a receiver. If the receiver actually is used to drive the speaker. Okay, the signal from for example, your TV actually is very, very, very small. You can, if you directly connect your signal from your TV to a speaker, the sound will be very small, very low. Okay, because the current is very small. So how can you use a small current output from the TV to drive a high current speaker to make the sound larger and louder? You have to use a receiver. So the receiver actually is a kind of amplifier. It amplifies your signal, the signal from TV. Okay, it's a very small, low current signal. And the receiver actually uses amplifiers to amplify the low current signal to a high current signal. And that high current signal will be output to the speaker and to make louder sound. Okay, so that's the usage for amplifier. Okay, so let's just skip this. All right, so so in this chapter, actually, we introduced many electrical components. Okay? So so here are some concluding advice. Never leave inputs floating. So you want to use pull up, pull down resistors, right? And ensure that all of the grounds in your circuit are connected to make sure that you don't burn your circuit. Okay, and remember to power your chips with the correct voltage level. Okay, and don't assume that a new diode, FET, BJT, or logic gate has the same pin. So you have to read their manual, okay, to know what pin it is. It has. Okay, and layout as the previous component that you use. I mean, this should be the same. Okay, just like programming. So when you build a circuit, you have to test it. You have to use a breadboard to make a prototype, and you have to test it. Okay, and never leave the circuit. I mean, when you, for example, for our project, okay, so you use Raspberry Pi, and actually the Raspberry Pi is an open circuit for the Raspberry Pi I gave you. Okay, that means never before you power your Raspberry Pi, you have to make sure that there are no metal on your table. Okay, because if you have metal, that will short the Raspberry Pi. Okay, that will burn the Raspberry Pi. Okay, so you want to avoid that. Okay, so so you want to read this carefully to make sure that whenever you make your electrical circuits, you don't you make it correctly, and you don't burn it, you don't hurt yourself. Okay. And don't assume that components have exact or consistent values. Okay. So in particular, transistor gains and resistor ranges. In fact, for resistor, for example, they have a range. They have a like a 5% range. Okay. All right. So for this chapter, actually, we introduce certain electrical components. So in the future, when we work on our project, you don't feel, you at least you have some knowledge about the components that you will expect. Okay, so that's something very important for computer science major students, because you don't have this kind of electrical engineering background. Maybe for these two classes, you think you may consider this as very boring, but actually it's very important for you to prepare for your project, because by having the knowledge of this basic electrical components, you have the idea on what kind of what is a circuit, and what you're supposed to do when you have a design, what kind of components you can choose from, and what kind of activities that you want to avoid to destroy your circuit. Okay, so that's something that we covered in this chapter. All right, so do you have any questions? Don't forget to type in your full name in the chat, so I can take the attendance for this class. Okay, and like I've said, I will go to the lab on next Tuesday during the class time. So you can go to the lab to pick up your components during that time. So so that way you can work on our future project in your home without the need go to the campus. Okay. Any questions?
Yes, sir. Which is going to be the room number?
It will be 222. I will send you an email to let you know.
Okay, thank you.
Yeah. Mm-hmm. All right.
Is this project going to be done in groups?
I don't know. For this pandemic situation, I don't know. If you like working in group, it's okay. I don't oppose that. I'm okay with group project.
Okay, and on Tuesday, will you be teaching on campus?
No, I will. I will not teach. I just go there, and you go there. Pick your.
Are you going to have class on Tuesday?
Yeah. So we don't have this Zoom meeting on Tuesday. So you just go to campus, go to room 222 to pick up your components at that time. Okay?
Thank you.
Okay. All right. Okay, so if you don't have other questions, that's it for today, and I will see you on Tuesday.
Okay.
Okay, bye-bye.
Have a nice weekend.
You too.